I'm going to talk about polynomial functions and absolute value functions. I'll assume that you know what polynomials are. I'll also assume that you know what an absolute value is. If you don't, I would encourage you to watch my videos on those topics. Okay, let me start by talking about polynomials. So I'm going to type out actually an important fact about polynomial functions that you should know. All right. The number of zeros of a polynomial function is less than or equal to the degree of the polynomial. All right, let's make sure we all understand what that means. So the degree of the polynomial is the biggest exponent. All right, the zero of a function, those are input values, traditionally referred to as x values, that correspond to a function value of 0. Okay, so the number of those zeros is less than or equal to the degree of the corresponding polynomial for a polynomial function. Let me show you some examples. Okay, here we have a polynomial function with a polynomial of degree 1, so we would expect it to have either no zeros or 1 0, and it does have 1 0 because f of 1 is equal to 0. Okay, here's another example. So this g is a polynomial function of degree 2, so we would expect it to either have no zeros, 1 0, or 2 zeros. And in fact, it has 2 zeros because g of 1 is equal to 0 and g of minus 1 is equal to 0. Now let me repeat that the number of zeros does not always equal the degree of the polynomial. All right? For example, look at the function h. There is a polynomial function of degree 2, and that has no zeros. Okay? So the number of zeros can be less than the degree of the polynomial for a polynomial function. Okay? Now let me work out a problem. Give me a minute to draw a graph and then we'll continue. All right, so I've drawn a graph that corresponds to the graph of a polynomial function. And let's see if we can answer some questions about the corresponding polynomial function. So what are the zeros of this function? Well, the zeros are the x values that make the function be equal to 0. In other words, they correspond to points where the y value is 0. So the zeros include the x values minus 2, 4, and 6. All right? And the degree of the polynomial, if the degree was denoted by the variable n, then n is greater than or equal to 3. We don't know for sure that the degree is 3. We know that it's at least 3. It couldn't be a second degree polynomial, for example. If we wanted to know the y-intercept, we can read that from the graph. That occurs at y equal to 2. If we wanted to know what intervals correspond to positive function values, we could answer that question from the graph. So between -2 and 4, or for x values greater than 6, right? So those are some questions that we could answer simply by looking at the graph of a polynomial. Now, I'd like you to do a similar exercise. So give me a minute to draw a graph, and then I'll ask you some questions. All right, so if this is the graph of a polynomial function, I'd like you to answer the following questions. I'd like you to find the following items. Find the zeros of the polynomial function. Find the minimum degree of the polynomial corresponding to the polynomial function. Find the y-intercept, and also find the intervals with respect to negative function values. All right, so pause the video and try to find those items now, if you like. Okay, so I'll go ahead and work it out also. So the number, the zeros, there's 4 zeros. Let me list the zeros. They include the x values 0, 4, 8, and 12. The minimum degree is, because we have 4 zeros, then the polynomial has to be of degree 4 or bigger. The y-intercept is y equal to 0. The intervals with respect to negative function values, so that would include x values between 0 and 4. So x could either be between 0 and 4 or between 8 and 12. All right? So I hope you got those answers. Now I'd like to shift gears and talk about absolute value functions. Here are some examples of absolute value functions. All right. Now, when you think of absolute value functions, I want you to think of functions that tell you the distance from the origin of a set of points. Okay, so let me say it again. When you think of absolute value functions, I want you to think of distance functions, functions that are giving you the distance from the origin of a set of points. All right? So let me show you how that will help you to understand how to solve certain problems involving absolute value functions. For example, what if we wanted to know the x value of an absolute value function that would make the function equal to 3? So suppose f of x was equal to the absolute value of x, and we wanted to know what x values would make that function equal to 3. All right? Now keep in mind that this function represents the distance from the origin of a set of points. So ask yourself, what points on the number line are a distance 3 away from the origin? Okay, now you might say the point that corresponds to x equal to 3, and you would be right. But can you see that there's another value on the other side of the origin corresponding to x equal to minus 3? So if f of x was equal to 3, then the solution, the x values that would make it equal to 3 would be x equal to plus or minus 3. Okay, and we were able to find that by thinking about distance. Okay, suppose we had a function, absolute value function g of x that was equal to x plus 2. And we wanted to know what x values made that function equal to 7. G of x equals 7. Okay, again, thinking about distances from the origin, we want either x plus 2 to equal 7, or just as well, we want x plus 2 to equal minus 7, right? So now we can solve both of those cases. All right, and so that's how you solve these types of problems. So the function g is equal to 7 when x is equal to 5, or when x is equal to minus 9. Okay? Now let me have you try an example. Would you please tell me when are the x values that make this function equal to 3? So h of x equals 3. Pause the video and try to solve that now, please. Okay, I'll go ahead and solve it myself. So we want the function equal to 3. So that means that we want the absolute value portion equal to 7. And that will occur when 2x minus 3 is equal to 7, or when 2x minus 3 is equal to minus 7. Okay? So we solve both of those cases. So x is equal to 5 or x is equal to minus 2. Both of those conditions will cause, or both of those x values will make the function h evaluate to 3. All right? Now, we can also deal with absolute value functions that involve second-degree polynomials. Let me show you an example of that. So suppose we had m of x was equal to the absolute value of x squared minus 4x minus 5. And suppose we wanted to know what x values made the function evaluate to 7. Okay, so we know that we can have the inside expression equal to 7, that's fine, or we can have the inside expression equal to minus 7. Both of those situations are fine. So let's solve both of those cases. So I'll subtract 7 from both sides. And let's see, x minus 6, x plus 2 is what that side factors to, what that quadratic factors to. So we know, therefore, that x is equal to 6 or minus 2. Okay, and then the other side, we get, let's see, adding 7 to both sides, we get x squared minus 4x plus 2 equals 0. And now we need to use the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. That gives 2 plus or minus, and I can divide what's inside the square root by 4. That's the same as dividing the whole square root by 2, and that gives me the square root of 4 minus 2. So that gives 2 plus or minus root 2. So for the set of all the answers, we have minus 2, 6, and 2 plus or minus root 2. Okay? Now I'd like you to try a similar problem. Suppose p of x is equal to the absolute value function, the absolute value of x squared minus 2x minus 1. And I want to know where px is equal to 2. All right? I want to know what x values make px equal to 2. So pause the video and try to solve that now, please. Okay, so I'll go ahead and do that. I'll go ahead and solve it now as well. So we need the inside quadratic to equal 2, or we need the inside quadratic to equal minus 2. And let me go ahead and solve both of those cases. All right, so x is equal to plus or minus 1, or x is equal to 3. All right? Now, we can also solve inequalities involving absolute value functions. So let me show you an example of that. Suppose z of x was equal to the absolute value of x. And suppose we wanted to know intervals such that the function was greater than 3. So ask yourself, where on the number line do the points have a distance from the origin greater than 3? Can you see that that corresponds to points with x values that are greater than 3 or x values that are less than minus 3? All right. Suppose we wanted to know x values such that the function was less than 2. So think about where on the number line is are the distances of the points from the origin less than 2. Can you see that that occurs for x values between -2 and 2? All right, let's now do a more complicated example. What about if we wanted to know where, let's say, the function w of x, which was equal to the absolute value of 2x plus 3, we wanted to know where function values are less than 6. Okay, so I know that points on the number line where the distances are less than 6 from the origin, that corresponds to x values between -6 and 6. So 2x plus 3 has to be between -6 and 6. All right, so let me subtract 3 from both sides. Actually, from all three parts. And now let me divide every part by 2. Okay, so I get that if I insist on the function values being less than 6, then I want to focus on the interval with x values between -9/2 and 3/2. Okay, now I'd like you to try an inequality problem involving absolute value functions. Involving an absolute value function. So suppose b of x was equal to the absolute value of 2x minus 3. And suppose you wanted to know x values that made the function greater than 5. Okay, so would you please pause the video and try to solve that inequality. Try to simplify that inequality. Okay, so I'll go ahead and do that. So we need the distance from the origin to be greater than 5, so that'll occur when 2x minus 3 is greater than 5, or when 2x minus 3 is less than minus 5. So let me solve both of those cases. All right, so putting it all together, we get that x for the function values to be greater than 5, we want to focus on x values that are less than -1 or x values that are greater than 4. And by the way, it wouldn't hurt to check your answers by plugging in some values. So a value less than -1 would be -2. So plugging it into the function, b of -2 is equal to 7. That's bigger than 5. An x value bigger than 4 would be, let's say, like 10. So b of 10 is 17, which is also bigger than 5, so that checks out. Okay? Now I'd like to talk about the graphs of absolute value functions. All right? And I'm going to make a request of you. I would like you to memorize the graph of the absolute value of x. I would highly recommend it because lots of absolute value functions are going to be similar to this graph, and they're going to be based on this graph in various ways, okay? So the shape of the graph of the absolute value of x is as shown there. So it corresponds to a V shape, the letter V, okay? Now I'd like to do a problem involving the graph of an absolute value function. Give me a minute to finish a drawing. All right, so this is the graph of an absolute value function. There's lots of information we can extract from the graph. So x values where the function is equal to 0. If you want the function to be 0, that occurs where x is equal to 1 or when x is equal to 1 or when x is equal to 3. Okay? If you wanted to know where the or what the y-intercept was, you can get that from the graph. That occurs with respect at a point with respect to y equal to 4. And furthermore, if you wanted to know x values that corresponded to function values less than 0, that would function values less than 0 correspond to x values between 1 and 3. Okay? Now, I'd like you to do a similar exercise. All right, so using just this graph of an absolute value function, I'd like you to try to find the following. Find the zeros of the absolute value function, find the y-intercept of the absolute value function, and find intervals where the function values are less than 0. All right, so pause the video and try to find those items, please. Okay, so I'll go ahead and work out also. So if you want the function to be 0, that occurs where x is equal to 2 or x is equal to 6. The y-intercept, that occurs at the point with respect to y equal to -4. And intervals where the function values are less than 0, that would include, or the function is less than 0 for x values that are less than 2 or x values that are greater than 6.